Now let's see what is turning moment diagram. A turning moment diagram is also known as crank effort diagram. It is the graphical representation of turning moment or the crank effort or the various positions of the crank. We know that as the crank is rotating, the theta value is changes, and according to this relation, the value of turning moment developed at the engine crankshaft is also changing. The plot between the variation of this theta angle, that means angle turned by the crank, and the turning moment developed is called as turning moment diagram. In this diagram, we will take as ordinate, at ordinate we take turning moment, and at abscissa, that means at x-axis, we will take our crank angle. This relation, this terminology is also known here. Already studied about this. Fp is the piston effort, R is the crank radius, and is the ratio of the length of the connecting rod to the crank radius. Theta is the angle turned by the crank. You can see here, this is the turning moment diagram for double acting steam engine, and you can see here that the turning moment in the first half rotation of crank, that means when theta varies from 0 to 90 degree, the turning moment increases. At when the theta is 90 degree, the turning moment reaches at the peak point. And as the theta varies from 90 degree to 180 degree, turning moment is decreases, that is torque is decreases, and again it will becomes 0 when theta is 180 degree. You can substitute the value of theta 180 degree here, and you will get a 0 value of this component. So the turning moment is also 0. Similarly, in remaining half cycle, turning moment again reaches at the peak value at the point small d, and again becomes 0 when the revolution is completed. That means the crank again move towards at its inner dead center position. Now, in this turning moment diagram, we can assume that the engine has to work for a mean resisting torque. That mean resisting torque, the mean torque between the maximum and minimum value of the torques. This is the maximum value of torque. This is the minimum value of torque. This is the mean value of torque. This height, abscissa, this height, that is ordinate of this turning moment diagram, shows the mean torque of the engine. Basically, the work done by engine is equals to the T into angle turned by the crank for any small interval. We can integrate it from the complete value of theta equal to 0 to theta equal to 360 degree to get the total work done during a cycle. Now, this work done is basically the area under the turning moment diagram. Okay, this area is basically the work done during the cycle. And the area under this mean torque, that means area under this AFEO, I will erase, I will clear the figure for you once again. Area under this rectangle AF small a small e is the mean resisting work done to engine. Okay. When the turning movement diagram is negative, that means the engine is absorbing the power. And when the turning movement diagram area is positive, that means the engine is developing the power. So you can say for this mean effective torque, if the turning movement diagram moves above the mean effective torque, mean resisting torque, then it is the power developing phase. And here you can see the flywheel or the rotating component of engines are accelerating. If the turning movement diagram is below this area here, in this case, in these situations, the rotating component are deaccelerating. Okay, so the net accelerating torque on the rotating parts is given by the difference of the torque at any instant of time, say t, and the mean resisting torque. So T minus T is the net effective accelerating torque on any rotating part of the engine. Basic rotating part of the engine is flywheel. So when T minus mean is positive, that means, as I said, if the turning moment at any instant is more than the mean resisting turning moment, then the flywheels are accelerating, and if the turning moment value is less than this mean value, then the flywheel is decelerating. Okay, so in this figure we can see all the variations of the turning moment of a single cylinder double acting steam engine. Now we'll see the turning moment diagram for 4-stroke internal combustion engine. Now here we are observing a turning moment diagram for the 4-stroke cycle internal combustion engine. During the suction stroke, which is the first 180-degree of the crank rotation, that means piston is moving from top dead center to bottom dead center or inner dead center towards outer dead center. As the piston moving downward, this pressure inside the cylinder is less. Therefore, this is a negative loop is formed here. This negative loop represents that this is absorbing the energy. That means the work is approximately done on the engine gases. But after that, the work is positive, but still below the mean resisting torque. So here the power is not developing in the engine. In another stroke, that is your compression stroke, during this stroke a higher negative loop is formed, which shows a higher energy is supplied to the gases to compress them. That means we are performing work on the system. That's why this energy is negative. And after this, after the end of compression, as the spark is provided or diesel spray is provided, then the combustion is started, and as the combustion is started, the forces increases because of the gas pressure, and the turning moment crosses the mean resisting torque. That means at this point we are having the generated excess power. The excess power is stored in the flywheel, which we discussed later on. Now, after the combustion stroke or working stroke, again the exhaust is negatively, slight negatively. So this is the turning movement diagram for internal combustion engines. You can see here loops below the mean resisting torque are basically the loops in which the power is consuming, and the loop which is above the mean resisting torque where the power is producing in the engine. Okay. Now we will see the turning moment diagram for a multi-cylinder engine. So here is the turning moment diagram for a compound steam engine having 3 cylinders. You know that in a compound steam engine, the exhaust of one cylinder goes into the as a inlet of lower pressure cylinders. So here you can see this is the first cylinder, which is the high pressure cylinder, this green one, and this blue one is the intermediate pressure cylinder, and this pink one is the lower pressure cylinder. The steam comes from the boiler and goes into the higher pressure cylinder, expand there. Exhaust of this spring goes into the intermediate pressure cylinder and then to the lower pressure cylinder. The cranks angles of these 3 cylinders are corrected at 120 degree to make the balance, proper balance. Here we can see a separate turning movement diagram for each cylinders. For cylinder 2 and cylinder 3. And the net resulting turning moment diagram for these three-cylinder engine is like this. Okay, you can see a continuous fluctuation of peak and valleys about the mean torques. So these are the study of some turning moment diagrams for single cylinder steam engine, double acting steam engine, internal combustion engine with 4-stroke, and the turning moment diagram for multi-cylinder engines. Similarly, for multi-cylinder IC engines, we can draw this turning moment diagram by combining the turning moments developed by the E cylinders and maintaining the maintaining a proper angle between the turning moments. You can see here, this is two cylinders have some difference. So in this manner, we completed the turning moment diagrams for different cylinders. Now in next lecture, we will introduce flywheel and see the fluctuations of energy between the in turning moment diagrams, and how we can determine the dimensions of flywheels, as well as what are the various characteristic parameters for the designing of flywheels. Thank you. If you have any doubt or query related to this particular class or any topic of this subject, you can ask us. You can send your doubts by the WhatsApp or mails at the numbers given below. Thank you.